Hey, welcome to 24th class meeting of EECE341, Introduction to Communication Systems. I've just told you about the attendance rule and also about the final exam date and time. So please send me an email with some evidence that you cannot take the exam in these 2 slots. Otherwise, I will announce the fixed final exam date and time on next Monday. About voluntary project, let me repeat. Your topic must be approved before the final exam via email confirmation by me. Topics must be related to this course, not related to signals and systems, not related to probability and random processes, not semiconductors. It must be related to some communications. Got it? Messages from instructor is always the same. Last class meeting, I just spent 15 minutes, so I will just regard it as the review for today. We are covering chapter 5, but as I told you, we are going to move chapter 12, information theory and coding, and I'm also giving you some flavor of this information theory and coding in this chapter 4. So what was the most important block diagram in chapter 4? Communications problem is to design jointly the transmitter and receiver. And between transmitter and receiver, there is a channel. And at one end, you have an information source, and on the other side, you have an information destination or information sink. So please remember this one. Of course, this is one of the simplest communication problem setting. Sometimes, as I once told you in this course, if you just see single source, think about what if, or why not 2 sources, right? Or why there is only 1 source. Think in this way. As I emphasized, our language, Korean language, as well as Japanese and Chinese, does not have so-called article, 관사. So we are, in many cases, ignoring whether something is singular or plural, something like that. So you have to revise your brain. So whenever you see a single block, what if there are 2 sources? So it's possible that you have 2 sources accessing the channel, computing the resource of this channel, and want to get to its own message here in the information source, sink. Sometimes you may have 1, 2, and many sources sharing the same channel. And all the messages compete to get to the destination. Sometimes you have multiple destinations, but still 1 channel. And sometimes your messages, your sources wants the messages to reach both of the destinations. Sometimes source 1 wants its message well decoded in destination 1. Source 2 wants its own message decoded well in sink 2, something like that. There are many possible communication situations. However, let's focus on the simplest one. So think about the single source, single destination case where you want to utilize some communication channel. This channel may admit discrete sequence. This channel may generate continuous time signal. So problems vary. There are many different types of problems. However, we always do something like this. we want to jointly design these two boxes. Sometimes it's called transmitter, receiver. Sometimes it is called encoder, decoder. So your communication problem is always a joint optimization of the pair of encoder and decoder so that your message is reaching the destination reliably. This is very important. And securely. Once I gave you some stunt like, okay, let me send you all the knowledge in the world to you right now, something like that. So I just sent you all the knowledge, but nothing is received. So transmission rate is not the only performance metric. Sometimes if you want to send message very fast, your messages may not be decoded correctly. So just not the transmission rate, but the reliability is very important. Second, in many cases, you do not want your message eavesdropped by other person, listened by other person. You do not want your message be heard by unintended receiver. So reliability and security, or how do you say that? Cryptography is very important in communications and has been important. So probably some of you in especially computer science and engineering department may have interest in this part. How can we make our communication more secure so that my information is not be decoded by unintended destination, something like that. So remember this figure. Even though this is the simplest communication scenario with only one information source and only one information destination, it may serve you as a mental model from which every possible other models for communication may spring out. Got it? Anyway, so let me just proceed for today's work. So last time we studied the different types of line codes. And line codes are simplest modulation method, encoding method, such as it admits bit sequences, logical bits, and it generates some continuous time signal. Why we generate continuous time signal? Because we mostly consider radio communication or electrical communication, where voltage and currents, its variation conveys the message. So there are many different types of line codes. So even though I say line encoder, its output, even though you have a same input sequence, output may vary a lot. And of course, in this case, you may want to generalize like this. Can you have some encoder, such as you have more than one bit sequences? So you may just abstractize it as a vector valued bit sequence. So Bn is Bn1 and Bn2, and each Bni is either 0 or 1, something like that. So whenever you see 1, what if there are 2? Okay, so sometimes you may have many parallel bit sequences, and sometimes you have only one continuous time signal, sometimes 2 signals, sometimes m signals, something like that. Of course, I'm not going to talk about this generalization in this course. So we are just focusing on the simplest case. Got it? Of course, there are other possible generalizations. For example, this Bn is not restricted to either 0 or 1. It may be 0, 1, 2, 3. It may be 0, 1, 2, 3, 4, 5, 6, 7. In that case, your waveform may differ a lot. Got it? Anyway, line encoder is the simplest conversion rule from a sequence of bits to a continuous time signal. Now, as we talk about, sorry about that. Yeah, here. Power spectrum and self-synchronization. As you've studied in some circuits, digital circuits course, some signals has, for example, let's see this. It has rising edge and falling edge, right? And these rising and falling edges may be utilized to synchronize your signal with receiver. So, for example, among these 6 different line codes, which one provides better synchronization scheme than others? So let's use our eyes, and in this case of consecutive zeros, here there is no rising and falling edges. So if you use none return to 0, then what happens? Your rising edge, falling edge detecting method for synchronization may not work well if you have very long consecutive zeros or ones. However, if you have polar return to 0 or Manchester code, you regularly have rising and falling edges. Okay. Of course, here, in this case, there is no edge. But you are almost guaranteed, that in the middle, you always have some edge, right? So the author of the book wanted to talk about synchronization capability of each line code. So depending on your choice of line code, sometimes the receiver may easily synchronize itself to the incoming signal. That is self-synchronization. Now, this is in time domain. In the frequency domain, we are mostly using so-called spectrum analyzer. So I've brought one picture here. And there are many big manufacturers such as Keysight, formerly Agilent, and formerly Hewlett-Packard. Sorry, Hewlett-Packard. By the way, if I say the company's name Hewlett-Packard, you may just regard it as some server manufacturer, computer server manufacturer. However, its origin was not that. Actually, Hewlett-Packard was this measurement equipment company. And when the computer generation has come, this company started small subsection to manufacture personal computers and notebooks. And that branch grew too big. And they separated the business and then sold this measurement part, and it's renamed as Agilent. And then again, in some way, they renamed their company to Keysight. So this is one company. And another one is this Rohde & Schwarz. Of course, there are other many good companies generating high quality spectrum analyzers or sampling oscilloscopes. Some company name is some Roy and some others, Rigol, or there are many other companies. Probably you never know, and you may never knew if I do not say that. Actually, Samsung Electronics once had a joint venture with HP. So, for example, if you join some communications related research lab in your graduate study and open a very old closet and see 30 years old equipment, some equipment has here, not HP, the mark SHP. It's Samsung Hewlett-Packard. So Samsung Electronics manufactured this measurement equipment. And also, sometimes Gold Star, you see, LG, formerly Gold Star, Kumsung, also manufactured some measurement equipment. When I was an undergraduate school, I purchased myself an oscilloscope manufactured by Gold Star. And I used the probe to do the experiment in my home, every possible electrical and electronic device. And of course, there was sometimes something like pong type thing, and my mother blamed me a lot about this power outage. That's what I remember. Anyway, so what is a spectrum analyzer? There are many buttons and knobs, dials, and one key is that you have a screen where this horizontal axis means frequency. So spectrum analyzer actually measures power of the incoming signal. So here you have a connector. So for example, you have some power amplifier and then you connect that. And here the power amplified signal goes in and this equipment measures the power spectral density. The theory is actually very simple. Inside of this power spectrum analyzer, you have some variable width, bandwidth filter, and also tunable frequency filter. So this F0 can be changeable, and this bandwidth is also changeable. And another thing is that here, duration of this power meter is changeable. So if you apply an RF signal, what does this equipment do is that depending on your preset, you have input here. It changes the width of this passband filter and this range of F0. So actually it sweeps slowly, okay, to measure. And also this power meter duration is given. And then here, this is frequency, and this height is watts per hertz. So if you integrate this signal from here to there, so suppose this is some capital S of F, means spectrum as a function of F, you integrate that function, then you have the power between these two frequency points. Got it? So watts per hertz times hertz, right? So this in hertz and this in watts per hertz, then you have watts, which is power. Got it? Of course, this is an approximation because the power meter accumulates kind of energy and mathematically speaking, divides by this T. So what we usually do is that our signal is kind of stationary. And the definition of stationarity is complicated, and I hope you learned in 전자수학 A, the EECE341. But anyway, I'm not going to tell too much about that. what is important is that there is a very basic measurement equipment called spectrum analyzer. So, for example, in our labs for communications and network, we have spectrum analyzer in each table because that is one of the most fundamental equipment for the such experiment, for such a lab. Anyway, long ago, this was huge. Even though the front panel size hasn't changed, the thickness significantly reduced this thick to that thick. So those who take the lab course have seen that Rigor spectrum analyzer is this thin. How this has been possible? Because most of the analog components is now replaced by digital components. So the measurement equipment itself has very fast analog to digital converter, very accurate and very highly calibrated. So the calibration error is minimized. And then what they do is now they sample the signal, they store and compute the power spectral density mathematically. They do no longer use some power meter. So the significant change has happened. Before, when this HP and SHP and Gold Star manufactured these equipments, there were two equipments on the lab bench. One was the oscilloscope, and the other was spectrum analyzer. So we had to purchase two equipments. But usually now we have only one. Why? Because anyway, this spectrum analyzer samples the signal. So if the sampled signal is directly displayed, it's an oscilloscope. So now the HP and Keysight actually no longer has two different equipments. They had only one. Where it is? I put it here somewhere. Not this one. Okay, this is old oscilloscope. But now you have this very compact single measurement equipment, and this is called the signal analyzer. So it does the function of oscilloscope and also does spectrum analyzer. And thickness is much reduced, and it's very lightweight. If you visit, for example, my lab, in the closet, there is a very old sampling oscilloscope or spectrum analyzer. And probably many of you may have difficulty in lifting it only by your power. You may need some assistance with your friend. That heavy. But now you can just grab here. Of course, this is this small. Grab here and even you swing it without any risk of dropping it. So what is one of my messages in this course? You must be friendly with your friend in other building of electrical engineering. Both of the buildings, they are very hardworking, smart people. Technologies evolve very fast. So once what was believed to be impossible is now possible. Anyway, here goes the topic we are going to study. So different line codes, which are some examples of digital modulation schemes, have different time domain characteristics like self-synchronization capability, but also in the frequency domain, they have different power spectrum. So if you use spectrum analyzer to measure the power spectral density of differently line cause signals, you observe different power spectrum. Now, how different are they? Is there any way to combine all possible spectrum in a single formula? And actually, there is. I myself do not believe this topic suits for undergraduate course because the power spectral density of digitally modulated signal, especially so-called linearly modulated signal, was a topic in the graduate level communications course. So I'm not going to derive the formula. I will just give you the formula and check which part affects our power spectral density in which way. So here goes the kind of general signal model. So our encoder, line encoder input was a sequence of bits. In our textbook, it is called A sub k because here A sub k may be 1 or -1, depending on which line cause you use. Okay, so here, let me say that, just a second. Yeah, here, today, I've slightly changed it, right? As you see, I said B, okay? So, and B is 0/1. And depending on different line codes, so let me modify this one. So first, the encoder converts whether to use 1 - 1 or 0/1. For example, here, right? Here, all the levels are zeros or ones. Here, all the levels are -1 and ones. Of course, here, levels may vary, but what's wrong? You may convert this one to -1 times some pulse. Could you turn it off? So anyway, what I want to say is this one. So given the sequence of logical bit 0 and 1, you convert it some way to some sequence A sub n. And then after that, interestingly, all these output of line encoders can be put in this form. I'm not saying that BK equals AK. I'm not saying this. Sometimes this is true, but not always. We need some simple encoding, and then the output signal can be put in this way. So a single pulse is repeatedly used to construct this signal. So whenever you see summation form, what do? You expand it. So let's rewrite. So when k equals 0, you have A0 P of t minus delta. For k -1, you have A sub -1 P of t plus kt minus delta. For A sub 1, you have P of t minus, t minus delta, dot, 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 dot. Right? So whenever you have difficulty in understanding summation formula, go back to the definition. Sometimes, even if you have integration, just recall your high school definition of Riemann integration. And then it can be well approximated by an infinite sum, and then it can be converted this way, right? Anyway, so what does this mean? A pulse P of t is shifted by an integer multiple of capital T. And then this encoded version of BK is multiplied. So let's see one example. Here, 0 is, so let's see NRZ. You have B. So AN equals -1 if Bn equals 0, and it is 1 if Bn equals 1. So this is the internal mapping rule from B to A, right? No memory there. Just you have input 0, then you have output 1. Input 1, you have output 1. And then, what is P of T in this case? If I ask you in the, for example, final exam, what is P of T given Manchester code, you must draw, right? So here, let's assume that this is time 0 and this is A 0, then you have what? You have 1, because in this case, this is 1, and height is 1, right? So 1 is converted to -1, so you have rectangular pulse here, so this part. And in the next time epoch, you have 0 again. Now you have shifted version of this P of T by capital T, which happens to be 1 here. So you shift that one, and now you have 1, which is converted to 1 here, and then multiplied by twice shifted version. So you have this waveform. Got it? What about this Manchester code? Let's have some exercise. So what is the mapping rule between Bn and An? Of course, there are two ways, actually. One is that, so one answer is like this. Same as this one. You claim this is the rule. Now, your P of T is what? So let's see. When positive 1, An is 1. So let's see this one. So you focus on that one. So what is your P of T? Your P of T is this one, right? So this pulse is repeatedly used in constructing your output. So for this one, since your A is -1, the signal starts from -1 and has rising edge and 1, like this, right? So this part is now constructed. What about second bit? Second bit is also 1, so you have that one. Third bit is 1, so you have that pulse. In this way, many of these looking different line coding schemes may be understood as what? As some after encoding of B sequence into A sequence, you have this common form. Okay. Now, we can derive mathematically the power spectrum of such a signal, assuming this A sub k has some mathematical probabilistic model. So as I emphasized, some of professors teaching this course requires the probability and random processes as prerequisite for this course. I didn't, because I didn't want to talk too much about random something. But it's almost necessary. It's necessary to have that background to understand digital communication, because in digital communication, we transmit some information from source to destination. That is the simplest case. And what is information? That is hard to define, but something that is uncertain at the destination. Otherwise, if this is certain, the message is certain, why we communicate? The reason why we communicate is because of the imbalance in information between the source and destination, right? And this imbalance of information means uncertainty is there in the receiver. And what is a mathematical method to model uncertainty? There are many methods, but one method is to rely on probability theory. So random variables, vectors, sequences, random processes, random fields, random graphs, those of ideas are crucial in counteracting the uncertainties confronted in every possible engineering and science problems. That's why once our postdoc required every freshman to take introductory statistics and probability and statistics course. I don't know whether it's continued or not, but one of our former president of the university required that for all the students, even he or she was to major in biology. And also, he enforced everybody to take a linear algebra, applied linear algebra, and of course, programming. I don't know whether that tradition is gone or not, but that was a nice move to make postdoc unique. But anyway, so given this model, with some probabilistic modeling on this A sub k, we can derive the power spectrum of this capital X of t in terms of P of t and capital T. This is important. And also the characteristic of AK. Fortunately, in many digital communications, this encoded version of our message bit sequence has nice property. A sub k plus 1, k plus 2, A sub k minus 1, they are random variables, and sometimes they are uncorrelated. Uncorrelatedness in Korean, 무상관, something like that, and correlation coefficient is 0, means whenever you compute the covariance, it's 0. And that gives us very interesting results like this. So here goes the final result. So this is the theorem. So the power spectral density, mathematically speaking, the power spectral density of that output of the line encoders may be always written in this form. So here first you have 1 over capital T, which is the transmission rate of the pulse. So whenever you see something like this, you decompose into factors. So first one is the transmission rate, pulse transmission rate, which is in per second or hertz. And what is this one? So we've found our pulse shape used in different line codes, right? Sometimes it was a rectangular pulse, or sometimes it was rectified sine pulse or something. What is this one? Fourier transform of the pulse magnitude squared. This is called energy spectral density of P of t. If you have taken signal intelligence systems, probably you heard about this. Where? When you studied Parseval's relation. There are probably around 4 Parseval's relation or Parseval's theorem. Among them is this one. Suppose continuous time signal has its Fourier transform pair, capital P of f. Then the energy of this pulse P defined as in the time domain, P of t magnitude squared dt equals this one. Of course, this is the simplified version, and more generalized version is called the Parseval-Planchara relation. But anyway, so what is this one? This is instantaneous power of the signal, and instantaneous power integrated gives us energy, because power times, what is this one? What is the unit of sec? Becomes joules, right? So energy. You have something integrated gives you energy. So whenever we have that situation, we call this one as something density. So this is energy density. Now, energy density is function of frequency. So this is called energy spectra, energy frequency density. Okay. Similarly, this is power spectral density, because if it is integrated, then it provides you power. And it's a function of frequency. So it's called power spectral density. And what is the third factor? What is the third factor? It is the characteristic of the A sub n sequence. And in many cases, this equals 1 for all f. In many cases, not always. Be careful. Now, if this is true, then our power spectrum just depends on the pulse transmission rate and the energy spectral density of the pulse. Of course, there needs some scaling, so we'd better say this one is proportional to. Now, let's see some power spectra. Spectra means spectrums for line-coded data. So the other cases, then NRG and where is split phase? This is Manchester, I believe, right? Split phase. Yeah, here, split phase has alias Manchester code. So we just focus on these two, right? Because other requires little bit complicated encoding scheme than this simple one-to-one memory list mapping. But anyway, so let's focus on these two spectral density. So NRG had pulse what? Let me remind you. NRG, non-return to zero, had pulse like this. And this split phase or Manchester code had, am I right? Something like this. So now let's have some intuition. So here you have 0, 0, 0, 0, 0. Suddenly you have 1. So some high frequency component and 1, 1, 1, 1, 0, 0, 0, something like that. Compared to the pulse shape of the non-return to zero line encoder, in the Manchester code, you have what? You have 0, 0, 0, so far the same, 1, so far the same, 1, 1, but sudden drop to negative 1 and sudden up to 0. So your just intuition attained from your signal system says that the pulse shape for Manchester code has much higher frequency component than the NRG case. Another one is like this. What is the average power of P of t? What is the integration average value of this one? Its average value is here 1, right? What about in this case? You have 0. What does that mean? P of f is what? So P of 0 equals simply P of t If you substitute 0 here, you have 1. So P of 0 in the frequency domain, P of 0 means the DC component here, and it has no DC. And since P of 0 is 0 here, energy spectrum at 0 is also 0 for Manchester code. That's why you have this null in the frequency domain for so-called split phase line encoder. So as you see here, depending on the pulse shape, you have different power spectral density. And if you compare this one directly, the pulse shape for Manchester code must have larger bandwidth. This is very vague at this point, but as you can qualitatively see, for example, suppose let's focus on negative 1 Hertz to positive 1 Hertz. Then outside this plus minus 1 band, what about the power spilled over this band for NRG? And what is the portion of the power spilled over this bandwidth in Manchester code? So we may just definitely vaguely say that Manchester code must occupy larger bandwidth than NRG. What is the benefit of apparently wasting our valuable bandwidth? In time domain, Manchester code may have much better property, like it allows self-synchronization at every midpoint because it provides rising edge or falling edge at every midpoint of each interval, right? So in communications, the bandwidth and some other property is always have trade-off relation. So if you want to have better some property, then usually, not always, usually you have to utilize larger bandwidth. So what would be the best case? Having the same bandwidth, you maximize some nice property, other nice property. That's why optimization theory kicks in. So as many of you already perceived now, every engineering subject, mechanical engineering, chemical engineering, electrical engineering, industrial engineering, they all study common subject, that is optimization theory. Sometimes computer science and engineering students may have more focus on discrete optimization. However, they study optimization. In industrial engineering students may have more focus on discrete optimization. However, mechanical and electrical engineering, chemical engineering students may have more focus on continuous optimization. So optimization is very important. Having the same level of some nice property, how can we reduce the bandwidth? That is an optimization problem. So this is my recommendation. Try to find some optimization theory class, whether it's about discrete optimization or continuous optimization. Your choice depends on your future sub-area to go. For example, you want to do computer science, definitely you'd better take discrete optimization course. If you want to do some control, electrical engineering, mechanical engineering, chemical engineering, probably you'd better find continuous optimization course and take it as early as possible before your brain is flooded by alcoholic beverages you poured in. Got it? Anyway, so I believe you now have some idea about power spectral density and different pulse shape used in line encoders may result in different power spectrum. And for other line encoding schemes, I think it's beyond the scope of this course. However, let me emphasize one. This third one, for unipolar return to zero, have something strange here. What is your guess? Direct delta functions. You have direct delta functions in mathematically defined power spectral density. Of course, your equipment, real-world equipment, may never show you direct delta functions. It may show very high spike in your display. Whenever you see very high spike, you must notice that, okay, probably if I derive mathematically the power spectrality, here is a tone signal or direct delta function, which translates to a pure sinusoidal signal in time domain. Why? So why do we have delta functions? And let's take a look at the time domain figure of our output. So here, this is our unipolar return to zero. Now, do you get why we have delta functions? Here, logical 0 is mapped to real number 0, and logical 1 is mapped to real number 1. So the output is 0, 0, 0. Of course, here, it has what? It has falling edge inside, but all 0 and falling edge. So let me ask you, what is the encoding scheme and what is the pulse shape for URG? Something like this. What is P of t? What is P of t? So let's focus on that one. So you have, so this is the pulse, right? The Fourier transform of this pulse, which has half the width of that pulse for NRG, is just what? Is stretched sinc function. So the first factor, the symbol pulse transmission rate, is fixed as t, 1 over t, which is 1. And see that this shape, of course, this is a little bit approximated, but just a stretched version of the power spectral density of energy. It is stretched. But why do we have these delta functions? It's because of the property of our encoded signal A. So this one provides us delta functions, periodic delta functions in the frequency domain for URG. Of course, I'm just giving you the idea very qualitatively. Quantitative derivation is deferred to your study of digital communications. I'm not sure whether Professor John Joseph will teach this one in our undergraduate digital communications course. It will be too much for undergraduates, but you now know what is there in digital communications. Now, here goes an interesting question. So we know that in communications, bandwidth or spectrum is the most important and scarce resource. Especially in radio communications, our signal may propagate a large distance, right? So in the short distance, cable must be better. But if it's over 20 kilometers, 30 kilometers, radio wave is much better as far as it's not absorbed by molecules too much, reflected by, scattered by too much obstacles. So that's why we do not, and some applications, we never have cables. For example, in spacecraft, we never have cable from Florida to International Space Station. So question is this one: how fast we can transmit information, of course, here, information, or information if you want information bits, given a bandwidth in real passband or real baseband. If it is real baseband, we are given the range something like that, and in passband, we are given, be careful, something like that. And as you notice here, we always, whenever we talk about electrical communication, we, especially practical, we assume implicitly conjugate symmetry of our signal. What does that mean? We use real valued signal because our electrical signal is a model of voltage of current, right? And you may say that, hey, this signal is different from that one. Well, you are right. However, we know that by using some equipment, you may just move down this part to here and move down that part to here. Then what's the difference between this and that one? So actually, mathematically speaking, having the communication channel with bandwidth W in baseband, real baseband, is the same channel, if its response is flat, same channel as this real passband channel with bandwidth W. Got it? However, in reality, there are huge difference between different choices of carrier. So let me draw another one. So suppose here the center is F1 and here F2, but still your bandwidth is W, and there you have bandwidth W. And the channel with bandwidth W has some center frequency Fi. So here F0 equals 0, F1 equals, for example, some 3 gigahertz, and here F2 equals 30 gigahertz, for example. As far as these channels, frequency responses are flat, for example, or same shifted version. They are same channels, mathematically. However, as I told you, we are going to use radio waves. And radio waves consist of electrical field and magnetic field. And these fields interact with molecules in our channel. For example, atmospheric molecules. Sometimes CO2, sometimes N2, sometimes H2O in the air interacts with our radio wave. That's why we utilize microwave oven, right? Some specific frequency interacts with H2O, the water molecule in our food. And this radio wave, microwave, kind of oscillates, radiates, oscillates this molecule a lot, so the energy is transferred to heat, and we have cooked food, right? So assigning different carrier frequency, center frequency, in the real world generates a lot of difference. And that is one thing. Another one is that if you have high frequency radio signal, what happens? Cables, wires, splitters, mixers, their prices goes up amazingly. So when you have 3 gigahertz radio, for example, you can manufacture it at the cost of $300. But if you want to build almost the same functioning radio at 30 gigahertz, suddenly your same equipment, same functionally speaking, equipment may price 100 times higher, 200 times higher. I believe that was one of the reasons why our 5G frequency range 2 equipments are not sold well. They are too expensive. There are too much RF loss leakage and a lot of troubles. But anyway, I'm not going to talk about that reality. In this question, I'm just asking, suppose you have mathematically equivalent real signal in, real signal out, band limited channel. Of course, continuous time signal input, real continuous time signal out channel with bandwidth W. Now, given that bandwidth, how much, how fast can we send our data symbols? Right? Because that is an optimization problem. For radio communication, our especially cellular service providers purchase some specific frequency band from the government. And it's hugely expensive. So you want to cramp a lot of bits inside that bandwidth. So let me ask you, how fast can we transmit? The answer is very simple, infinitely fast. But all the information will be almost, if it's bits, probability of error will be 0.5 almost. What does that mean? No information is transmitted. So how fast can we transmit information bits given W? Reliably will be a more proper question. Of course, if you add securely, then depending on the definition of security, your probably transmission rate will be reduced if you add more and more conditions. But for simplicity, let's think about this case. So you want to transmit bits reliably given bandwidth W. Find a solution. I'm not saying that you find every solution. Just there will be many different optimal ways to utilize that, right? So I'm asking at this point, provide me an optimal solution to do that. And whenever we talk about optimal, we have to define what is optimal. It is called optimality criterion. One of the optimality criterion is related to so-called inter-symbol interference. And inter-symbol interference is quite confusing terminology at all, because some professors define inter-symbol interference this way, the others in different way. Some textbooks say inter-symbol interference is that. Some other book says different. So let me vaguely say, let's just dissect this inter-symbol world, which means that between symbols, right? Then what is the symbol? If we recall our line encoder's output, which is written in this way, this AK is the symbol, got it? You may regard it, given our line encoder, in the output we have AK, right? AK is the symbol. So this interference concept in Korean is between or among these symbols. That is the term literally says. Okay? So interference among these symbols. What does that mean? So in order to make everything simple, let's think about what is that? Is it NRG? I believe so. Yeah. Suppose you have a non-return to zero signal, x of t. So as you remember, it is +1 or -1 for each length 1 duration. And the signal, mathematically speaking, has infinite bandwidth. We have 3 more minutes, right? Yeah. Infinite bandwidth. But in reality, there is no infinite bandwidth signal. Every wire, cable has some frequency response like this. What does that mean? High frequency terms is much more attenuated. So these sharp edges are smoothened. So this is what happens. For example, of course, in this case, it seems that you have capacitance component in your transmission line. So this charging up takes time, and this charging up for the negative takes time, something like that. So you have distortion, right? Now, sometimes if your transmission medium has a lot of capacitive component, your NRG signal, when it is transmitted through some channel, may look like this, right? Sometimes you have much more complicated one. So here goes examples. So this is time axis. These are time axis. And you have signals observed at your oscilloscope, sampling oscilloscope. So even though ideally this NRG must have sharp edges at each unit second, you have very smoothened version at the end of your transmission line. And for NRG Mark and unipolar RG, polar, and Manchester, you have very, very distorted signal. Now let me ask you, how can we reduce the error? Because error may be due to the distortion. Of course, if you transmit single pulse, probably you will have something like this, right? So the distortion here, right, will be due to the previous or next symbol. So these symbols are put side by side, and they are filtered kind of a low pass filter. So this time, in the time domain, the signal spills over. So even though your pulse P of t looks like this, after passing through a filter with impulse response H of t, it may look like that one, right? Then your signal X has P of t, but your output signal, say X tilde, has output pulse shape that one. What does that mean? If you have 1, 1, 0, then these pulses will be overlapped and summed. That is your output at the end of your communication channel. So definitely, vaguely speaking, definitely, you have, here, these pulses do not overlap, but here, they overlap. So in this way, you may interpret intersymbol interference as what? Before, the pulses didn't overlap. Now, the signal passes through a channel, especially band limited, they overlap and interfere each other. That is the simplest, but not precise definition or feeling of intersymbol interference. So what I want to say is that depending on the pulse shape, same channel may give you different level of intersymbol interference, right? For example, the pulse had very high frequency component, like in Manchester code. It will be much more distorted if you are given a very narrow band channel compared to NRG. because energy has around half the bandwidth, right? So have the feeling, have the intuition in your mind, given the same channel, depending on your choice of pulse shape in, for example, line encoder, you may suffer different level of intersymbol interference. Got it? Okay, that's all for today. Do not forget to send me an email about your availability on the candidate final exam dates and time.